Welcome once again, dear participants. Actually, the next session is will be taken by Professor Rohit Bhakar, sir, who is from MNIT Jaipur. He is professor there in the electrical engineering department. So probably he might join soon.
Yeah,
So
right.
actually,
I'm Rohit Bhakar.
yes, yes.
Um,
Is there anyone wish to ask something? Some of you from the participants might be knowing to Professor Rohit Bhakar, sir. He is very well-known personality in the field of power system. Basically, he is the head of the department also in the energy center there in the MNIT Jaipur, and he has have plotted one of its kind, and I must say first kind of MTech course in the energy management. That is kind of course with actually power with the management. So kind of a course which actually having the subjects like from the MBA, that is the management side, as well as from the electrical engineering or the power system side. So he has very wide experience, and he has good number of publications in journals like IEEE Transactions and IET elsewhere, Springer. So, so with this, actually, I wish to invite and I'll call to Rohit Bhakar sir. He will probably join within a few minutes. So please be here only in this meeting. Today in the first session, some of your participants, some of you might have the problem of joining the meeting. Actually, I have invited all the participants who have registered through that ATAL portal, but somehow there is some settings in the WebEx, and maybe I have not enabled that. That's why you may have this problem today. And from the tomorrow onwards session, I'll check that out, and it will rectify. It will be rectified. So probably from the next session onwards, you will be able to join directly without making you let in by myself. So at this time, actually, I need to make each and every participant to let in. So this is a very tedious process, and actually there are around 180 participants, and choosing everyone all the time is very tedious. So actually, this is the problem we are facing today. So from tomorrow onward session, you will not be have the problem of joining, because I'll send you the invitee link over your mail. So if you are joining through that mail only, then you will be directly become join this meeting, because there is no need to making me from let in. There is no problem. So I request once again all of you to please join the meeting through your registered mail only, which you have registered through in the ATAL portal. I hope you all have got the Google form that has been earlier posted in the chat of this meeting. So you may feel that your attendance will be marked from there. Every time I'll post one Google form there in the meeting chat only, and you simply fill that form by just typing your mail ID which through which you have registered in the ATAL portal. So you simply need to put your mail ID, your name, the expert who is presenting there. Actually, sir is joining shortly. Uh, yes, sir, sir, are you there in the meeting? Rohit Bhakar, sir, you are not audible.
Yes,
Perhaps you
yes,
have.
I can hear you. I hope I'm
Okay,
audible.
okay. All right, sir. All right. Thank you very much, and I welcome you, sir, in this 6 days online ATAL FDP. Actually, you have just joined, or you have joined around 2-3 minutes back.
2-3 minutes back I joined, I think.
Okay. All right, sir. All right. Actually, I was waiting that sir is going to join.
Okay, I've already joined.
Okay. Okay, all right, sir. Thank you very much for joining. I think I should start the proceeding because since it is about 8 o'clock and many of the participants are there in the meeting already. Around 110 participants are there, although the registered number of participants are 180 plus. I mean, around 190. So earlier session has been taken by Dr. Nishant Kumar from IIT Jodhpur, and he has just completed. And before that, we had one inaugural session wherein our college administration and university administration were there. So I think we should start the proceeding. So before starting your session, I wish to simply cite yourself, or I mean, I wish to read your biography so that the participant could be able to connect with you, and they will be able to know yourselves. So actually, the dear participants, welcome you once again in the second session of the day, second and the last session of the day. So in this session, Professor Rohit Bhakar sir, who is from MNIT Jaipur, will deliver this session. So actually, Dr. Rohit Bhakar sir is a professor in the Department of Electrical Engineering. He leads the Power Management Research Group, which runs first of its kind MTech in India, as I already said on power system management. I was, sir, before joining yourself, I was talking about yourself only that you have started one of its kind, and I must say, first kind of MTech program in the MNIT, and that too about the power system management. So that thing, I think this is one of its kind of MTech wherein power system with the kind of MBA people are there in this one. So management with power system, this is very much really interesting. So having a very wide research experience on multiple aspects of power and energy systems, ranging from system restructuring and markets, system operations and planning, decarbonized energy systems, digitalized and decentralized energy systems, grid integration of renewables, sector regulation, smart grid systems, risk management, net zero planning, and demand response mechanism. He had supervised over 12 PhDs and 45 MTech dissertations and published over 200 papers in top rated journals and conferences. He has collaborations with researchers from the UK, the US, Canada, Denmark, Germany, Spain, and China. He has secured multiple research grants of over rupee 100 million from international and Indian funding agency and the industry. Further, he has over 25 years of experience in teaching, including that of electrical engineering at undergraduate level and power system engineering and energy and environment engineering at postgraduate level. He has served as a member of State Advisory Committee, Rajasthan Electricity Regulatory Commission. He has served as head of Center for Energy and Environment, chairperson and vice chairperson of IEEE Rajasthan subsection, secretary of IEEE PS working group on distributed network charging and tariff structures. So this much of wide experience and wide, I mean, academic as well as research and administrative experience you have, sir. So with these words, I once again welcome you and invite you to please present yourself. Rohit Bhakar, sir, please.
Uh, Thank you. Dr. Ganesh, for inviting me. I hope I'm audible.
Yeah, yes, sir. You are audible, sir. Please.
I'll keep my video off so that internet connectivity doesn't become an issue.
Yeah, sure, sir. No problem.
Uh, Thank you, Government Engineering College, Bikaner, for inviting and organizing this event. Engineering College Bikaner, as you call it, and the university, which is now at the helm of affairs for this college. First of all, I'd like to understand the participants. I guess some of the participants are already PhD. Uh, some of them are
Yes, sir.
faculty
Yes,
members,
sir.
and
I
others.
wish to inform you that there are the participants from the various fields. Although most of the
Uh,
participants are faculty members, but some may be some research scholars from Tech and PhD. So, although I hope that 80 to 90% participants are faculty members, and that too from the different areas. Maybe some of them from computer science or some IT, some mechanical, electrical, civil
okay,
people are also there. So, this is all about the participants.
never mind. I'll try to make it simple for everyone so that everybody can understand it.
Yes.
The challenges that this course focuses upon are really relevant because now everywhere people are talking about renewables, people are talking about renewable integration, putting up solar rooftop, and I think people from Bikaner would be that is the place where most of the things are happening, the western part of Rajasthan, where most of the renewable generation in terms of solar generation is happening. So that makes it even more relevant to understand what really is happening. Uh, when we talk about power systems, broadly, those people who come from civil or computer science, we must understand that it comprises of a couple of things we always need to keep in mind. One, that electricity supply comes through a supply mechanism comprising of generation, transmission, and distribution. Generation, which primarily comprises of, it may be thermal in the case of countries like India, it may be hydropower plants, nuclear power plants, and over the last couple of decades, it is also significant generation that is coming up in terms of solar generation and wind generation. From those large power plants which are situated at certain specified places, like if you talk about thermal power plants, they are primarily placed in states where there is a lot of coal generation available, like Chhattisgarh, Bihar, and the areas around those. When we talk about hydropower plants, they are primarily based in areas where we have got the dams, where we are able to build large hydropower plants. If we talk about nuclear power plants, they are typically situated in areas where you have got which are far away from urban population, and there is water availability. Apart from that, if we talk about solar generation, that is significantly concentrated in Western Rajasthan, Gujarat, and certain parts of South India as well. Wind generation also, significant generation is there in Tamil Nadu, Andhra Pradesh, Gujarat, and Rajasthan. All this generation has to be, I'll just share this. All this generation has to be evacuated and
Participants, you please keep yourself muted.
Dr. Ganesh, I hope you are able to see the screen now.
Yeah, yeah, sir. It is visible, clearly
Okay.
visible.
The change of screen is also visible.
Yeah, yes, sir. It is changing.
Okay. Okay. Fine.
Thank you.
Okay. So all this generation has to be evacuated from those far off generation, trans, uh, transformed in terms of voltage levels from lower voltage levels, which is about 11 kV or 13.5 kV, to higher voltage levels, transported over long distances over those high voltage transmission lines like 132 kV, 220 kV, or 400 kV, or even higher than that, 750 kV. Thereafter, transforming it down again to lower voltage levels where utilization or consumption of electricity can happen. This happens typically at lower voltage levels. It could be at 33 kV, 11 kV, or 400 volts. That is the typical voltage that we use in our households. What are the changes that are happening in the grid when we start talking about renewables, when we start talking about sustainable generation and all these facets? Though a question that keeps on coming, which even at the policy level, which people keep on asking, is whether why don't we have all of generation coming from renewable? Why should we have thermal power plants, or for that matter, any other nuclear power plant? These questions keep on coming. People keep on asking at the policy level, planning level, as well as the system operation level. Different people have different ideas. However, there are technical challenges in allowing the whole of grid to become a RE grid, a renewable grid. What are those challenges? Where are we? Where are we heading towards? Possibly, I'd like to touch upon those issues over the next 1.5 hours. If at any point of time, if you feel that there is any doubt, feel free to unmute yourself and ask a question. That would be better. So there are certain phrases in this title. There's one is power system flexibility. Another one is RE rich grids. When we use the term RE rich grids, essentially we mean electric grids which are dominated by renewable generation. When we use the term power system, we primarily mean the system comprising of generation, transmission, and distribution, including consumption, and being able to think of this whole ecosystem as a single system. Because the intricacies of generation portfolio, intricacies of transmission line availability, and the demand profile makes an impact on how the system is to be operated. Flexibility, we all understand, is the ability to respond or to ability to make changes in view of, in consideration of the changes that are happening in the system which are beyond our control. So power system flexibility in RE-rich grids primarily focuses on issues that when we are trying to integrate more and more renewables into the grid, what are the challenges that the grid operation would face? What are the specific challenges of flexibility that would arise when significant RE penetration, when significant renewables get integrated into the system? Sorry. So this is sorry. So this is the broader framework of the class: conventional versus what is RE-rich grids, the need for system flexibility, the definitions, indices, measures, what are the options, what are the policy and market framework, and so on. I do understand, as Dr. Ganesh pointed out, these type of studies, they require an understanding of not only of engineering, but of good level of mathematics in terms of modeling abilities, and a significant understanding of market and policy framework. So significantly, these areas are areas where you need interdisciplinary understanding of things. And it requires working with a larger set of people to understand what all are the challenges. Just to take you through this journey, electricity, some of the points I'll read it out, and possibly some of the things you can make out. Electricity, it is the fastest growing form of end use energy consumption, meaning thereby that whatever forms of energy consumption that we are doing as of now, it is the fastest form. Other forms like oil, gas, or heat, they are not increasing. Their consumption is not increasing as fast as is the consumption of electricity. And presently, it is contributing to 40% of the carbon dioxide emissions that are happening through all energy sources. So it is a significant contributor to the carbon emissions as well. So that underlines the need to have more and more renewables in the grid so that carbon emissions are minimized while we are increasing the use of electricity in our daily consumption. World's electricity consumption is increased 25% over the decade 2009-2019. That is also a significant increase, and that continues to grow. Fossil fuel based electricity generation typically contributes 60% of the total generation worldwide. So, whatever we consume, out of that, 60% is still being produced by fossil fuel based generation, which would include coal based power plant, which would include oil based power plant, which would include gas based power plants. The challenges with fossil fuels availability, increasing fuel prices because of non availability at certain areas, global warming, air pollution, all these things they do affect the policymakers to shift towards generation which is not so which does not emit so much of carbon emissions, and that leads us to RE penetration, RE generation, which we use a term low carbon power systems, typically indicating power systems which supply electricity using low carbon sources of generation. On the right hand side, you can see there is a graph. It is a slightly couple of years old, but it does reflect the quantum of electricity produced by different sources. So if you see on the right hand side, significant quantum of electricity is being produced from coal, then from gas, some of it coming from oil, a part of it coming from nuclear, and significant portion therein coming from hydropower plants, and the others coming from wind, solar, and other renewables. So you can still see that the portion of electricity being produced by renewables is significantly low, and a majority of it is still coming from conventional power plants like coal, gas, oil, and nuclear. However, as we are moving towards renewable generation, the two technologies which have dominated the area of renewable generation is wind and solar. Wind, it's slightly costlier. Solar is becoming cheaper when we typically are situated in areas, in tropical areas close to the equator. Wind is significantly available on seashores, on and off the shores, and that is one of the areas where significant generation is happening. That is happening on European shores, where a large number of wind turbines are not only placed on the shore but as well as off the shore. Both the sides the wind turbines are there. India, relatively, the wind generation is not growing as fast. Solar generation is picking up at a much faster pace because of cost economics. The cost is somewhere around 2 to 2.5 rupees per unit, which makes it much cheaper as compared to wind generation, which comes somewhere around 3.5 to 4.05 rupees per unit. Over the past few years, the penetration of renewables, it is increasing from as high as 67% or even more than that in Denmark, 50% in Germany, 40% in Spain, 20% approximately in US. India also, it has increased by in a similar number, somewhere around 25% or so. The challenge with these renewable generation technologies is that these are weather dependent. These generation technologies do not produce electricity based upon when we need it. Their generation is simply based upon, let's say, for wind turbine, they will produce electricity when wind speed is high, when there is appropriate wind direction. Solar generation would produce when the solar irradiation is high, the ambient temperature is fine, and so on. So their generation from wind and solar would significantly depend on weather conditions rather than the quantum of fuel that we inject, because we don't inject any fuel. In case of conventional power plants, we are able to control the generation because the generation is dependent upon the quantum of fuel that we inject. In this case, we don't have any fuel and the generation is simply weather dependent. This being weather dependent, it creates challenges because weather is not a certain quantity. Weather in itself is an uncertain parameter. So when the weather, we don't know whether it will rain tomorrow or not, whether there will be clouds there or not, whether there would be winds blowing tomorrow or not. So these are uh, things which are not in human control. So also the generation is not in human control, and this creates significant uncertainties on how much generation would happen at any given point of time. So that creates problems for system operators, because at any given point of time in power system, the system operator or the people who are operating the grid, they have to ensure that whatever is the quantum of demand in the system, let's say at any given point of time the demand is 100 gigawatt, they have to ensure that the same quantum of generation is happening in the grid at that point of time. So in any case, they cannot allow a situation where the demand is 100 gigawatt and the generation is only 95 gigawatt. That is not a sustainable situation, because in that case, where do we get the 5 gigawatt from? So the balancing of generation and demand at every second is critical for system operation. And uh, it is so critical that even if there is a small shortfall in generation, the system frequencies would start falling from the standard values of 50 hertz in case there is even a small deficiency of generation. In case the generation is more than what is the demand, the frequencies will go above 50 hertz. So in all those cases, it is not a viable option to operate the grid at frequencies which are significantly divergent from the standard operating frequency, which is 50 hertz. So presently we operate in an era where the frequencies range between 49.5 to 50.05, 49.8 to 50.05. So that leaves a very limited band in which the system frequency can be operated, and that pushes the system operator to ensure that each and every second the generation is equal to the demand that is there in the system. And the problem is, the in the case of conventional power plants, they could do that because whenever the demand would change, they would inject that quantum of fuel into the grid. If the demand goes down, they'll inject less fuel. If the demand goes up, they'll inject more fuel, thereby ensuring that both the generation and demand are equal. So how things are evolving, what are the changes that are happening when we see the scenario change happening from conventional to RE rich grids? Conventional grids, as we just discussed, they are primarily fossil fuel based grids. Their generation is controllable simply because we control the quantum of fuel being injected. The only uncertain part in the conventional grids is the load. So as the load varies, we try to match the generation by injecting that quantum of fuel into the grid. The generation is reliable because we can control the generation at every point of time, though this creates significant carbon emissions, and there are high operation and maintenance costs associated with conventional grids as well. When we go to RE rich grids, where there is a significant share of RE resources, it is significantly dependent upon nature, which leads to a limited control over the grid. The challenge is, not only is the load uncertain, but the generation also becomes uncertain, thereby putting a pressure on the system operator to manage two uncertain quantities, one which is load and second which is generation itself. So trying to handle a system in which both the demand and supply are uncertain becomes a Herculean task for the system operator. To focus on exactly what is the level of the problem, we have started quantifying the value which we call as net load, which is effectively an indication of the overall load in the system minus the RE generation. Both these parameters are uncertain. So at any given point of time, whatever is the given load, let's say the given load is 100 gigawatt, RE generation is 30 gigawatt, then in that case, 70 gigawatt is the load that is to be met by all other sources other than the RE generation. So in this case, 70 gigawatt would be the net load. Let's say if the RE generation increases to 35 gigawatt, the net load would reduce to 65 gigawatt and so on. So this net load indicates the quantum of generation that has to be met from conventional power plants like coal, gas, nuclear, etc. This creates challenges for the system operator because with a limited net load, that is 65 gigawatt, rest of all the quantities in the system, the load and the generation, they have become uncertain. So with this, the generation, the controllable generation is has to be varied so as to ensure that whatever is the difference at any given point of time, it is balanced appropriately. This obviously makes the system uncertain and the parameters are always variable. Though the good thing is the carbon emissions are reduced, overall O&M cost in the system are reduced. But again, as I pointed out, net load uncertainty, this variability in the net load is a key challenge that the system operator has to focus upon. And that is where over the last 4 or 5 years, people, researchers, not only researchers, but system operators have also started focusing upon. Is there any doubt till now? Any question till now? If anybody has any question, else we move ahead. Anybody has any quick question? If none, then we'll go ahead. So here we come directly to the problem which possibly each one of us needs to focus upon and understand what are the challenges. I'll request attention of everyone. Very interesting graph, but very relevant. So if you understand this, you'll understand the whole of the presentation that I'll be taking after this. In this graph, we are indicating 4 parameters. One is the load, one is the net load, one is the wind, and one is the solar. To start with, the purple line, this indicates the load in the system. The load in the system during 0 hours, that is night hours, it is low. It increases somewhere around 4 o'clock in the morning. It increases to 6, 7, 8, 9 o'clock. It increases. It depending upon which part of the country we are talking about, it may go down, and we will have an evening peak coming into the system when everybody is using lighting. So there would be a peak coming up in the system, and again as the night falls, the demand in the system would also fall. This is a typical, it may vary, it is a typical load profile of the system over a 24-hour period of time. If you see, there's another graph, another plot, which is indicated by in this red dotted line, wherein the solar generation is 0 during the night hours. It ramps up during the morning hours from 5 to 8 or 9 o'clock. It starts coming up. It still continues, it ramps up at a very fast pace from in the morning hours, becomes stable, reaches a peak somewhere around 1 or 2 o'clock in the daytime, and after 4 o'clock, 5 o'clock, it starts going down, and by 6 or 7 o'clock, it is almost negligible. This is a typical generation curve for any generation power plant. Wind generation, on the other hand, is significantly variable. It is unpredictable. It keeps on varying during the day and during the night hours. So that is indicated by a blue line. So as we see, this purple graph indicates the overall load in the system. If we subtract from this load curve the wind generation and the solar generation, this will give us a value which is reflective of the net load of the system. The numbers may not exactly match, but the concept should match. You should be able to pick up the concept. So the net load at any given point of time would be the difference between the load in the system and the generation that is happening between wind and or the summation of generation because of wind and solar. It would be somewhat, we would have some net load during the night hours. During the morning hours at around 4 o'clock, as the demand increases, as the load increases, net load also increases, because even before the sun rises, there are certain people who rise before the sun. So the demand would start increasing even before the solar generation starts coming up. Some people wake at 4 o'clock, 4:30. So the demand starts rising up. The net load starts rising up. So as the ramping of the load happens, in a similar way, net load also ramps up. Solar generation starts coming at a slightly later time, 5 or 6 o'clock. So when solar generation starts ramping up, despite that the load increases in the system, the net load in the system that starts going down, because this is effectively the load minus the renewable generation. When the renewable generation ramps up, the net load in the system that is to be fulfilled by the conventional generators that starts going down. So this black bold line indicates the overall demand that is to be fulfilled by conventional power plants like coal, gas, and nuclear. During the daytime, the load remains steady, the solar generation is up, wind may vary depending upon a reflection of difference of those. The net load would continue going down. By 4 o'clock, it will continue to go down. After 4 o'clock, the solar generation significantly starts going down, and the demand starts increasing after 5 or 6 o'clock because of the evening lighting load. This leads to a situation wherein, while there was a significantly low demand on the conventional power plants at around 4 o'clock, the low generation has to be ramped up to meet the net load requirement in the system. It ramps up like anything. From 4 o'clock to 7 o'clock, the net load on the system would significantly ramp up. Beyond these hours, as the demand goes down, the net load in the system also starts going down. So, the interesting part to see is the difference in the profile of the load and the net load. When there was no renewable generation, the load in the system the variation in the load has to be met by pumping more fuel into the grid, or at these points reducing the quantum of fuel being injected to the grid. But the ramping requirement in the system increases at a very fast pace during these hours, morning hours, and excessive fast rate during these hours, which are evening hours from 4 o'clock to 7 o'clock. This is one of the critical challenges in the system. It is critical, as you see these times which come under the dotted lines. These are critical times when the grid has to be operated in such a way that the problem of the system is not to supply the sufficient quantum of energy, but the challenge is to ramp up the generation of conventional power plants from a very low minimum to a very high maximum in a very short period of time. This is the challenging proportion. This is like starting a bike or speeding up a bike from 0 kilometer to 100 kilometer per hour in a very short span of time. Not all motorcycles are made for those. Some of the vehicles that we use, they can be speeded up at a slower pace. They will increase their speed. Obviously, they'll increase their speed, but possibly they may take 1 minute to increase the speed from 0 to 100 kilometers per hour. There are new generation bikes. They may be able to increase the speed from 0 to 100 kilometers per hour, possibly in 10 seconds or 5 seconds, and so on. So, depending upon what type of bike we have got, which would have a different ramping ability. The new generation bikes would have a faster ramping ability. The old generation bikes would have relatively lower ramping capabilities. So, depending upon the ramping capabilities of the generation, we would be able to provide this ramping requirement in the system. Unfortunately, conventional power plants old conventional power plants have limited capacity to ramp up. So this creates a problem. that our coal power plants cannot suddenly increase, especially the old ones, they cannot suddenly increase the generation from a low value to a very high value, because if you start doing it, it will lead to high thermal stresses in the turbines, leading to failures in the turbine, which is a technical challenge that cannot be handled. This creates shortages in the system ramping capability, indicated by a figure, the change in generation divided by the change in time. This ramping, this, I would say, the angle of this, the slope of this indicated by del Pg by del T. Conventional power plants have got limited ramping capabilities. Some of the power plants, like gas power plants, they have got good ramping capabilities. Oil power plants, they have got good ramping capabilities. Coal based power plants, nuclear power plants, they have got relatively less ramping capabilities. So if your generation is predominantly nuclear or coal based power plants, your ability to handle these ramps would be significantly low. This is a typical problem with the Indian grid. Our generation is significantly based upon conventional coal based power plants, which render it technically insufficient ramping capability to meet the ramping demand in the system.
Sir,
This is the
actually,
crux of the problem.
am I audible, sir?
Yeah.
Actually, I have
Yes,
one
yes, yes, please.
doubt about this one. Actually, although it is not doubt, it is kind of discussion only. Since I
Yes,
can
please.
see on the slide that in between 7 o'clock to 18 of o'clock, there is the solar power generation, and that's why the net load is lower. I mean, very
Yeah.
lower, I must say.
Yes. Yeah.
So, in
Mhm.
that period of time, I mean, since the solar and wind both are not, supporting in the frequency regulation, and or I must say they don't have inertia, and that's why there is the problem of frequency excursion during this time. So,
Yes.
whether it will happen that in between this duration, that means 8 to 18, is there any problem of frequency excretion more than the other time, since there is the problem of inertia when we talk about the frequency part. So although there is
Mm.
the good amount of energy available in terms of solar and wind, but
Mm.
even then I think this will be very much prone to the change in frequency, although the
Yes.
load is low.
Yes. We need to understand why do we have this problem of frequency? When do we have this problem of frequency? What is the genesis of that?
Yes, exactly. If there is the, if there is not much amount of energy reserves available during
Yeah.
the higher
So
load.
let's say yes. Essentially, we would face challenges of frequency. Let's say lower frequencies when the
Yes,
demand is more and the generation is less, and of
yes,
higher frequency when the generation is more and the demand would be lower. So obviously, the point that I wanted to highlight is that uh, before we start focusing on the frequency is obviously issue that will come up.
yes,
But
sir.
even before we start focusing on that, the prime challenge is that system does not have the capability to provide that quantum of power. One. Second, it does not have the ability to provide that ramping. This creates a situation for sustained periods, like this period from 4 o'clock to 7 o'clock. For this period, inevitably, despite that the power plants are trying to increase their generation, they would be running the ability behind the demand. So essentially, this period is a period where there would be significant frequency exertions happening in the grid,
Yes, sir.
both from the perspective the grid would not have the capacity to deliver, and not only generation, but as well as the ramping ability is not there. We need to differentiate those, both the parameters, the generation and the ramping. These are two different parameters. It is something like a bike, which we say a 100 cc bike. I'll just give you an example to understand the problem. A 100 cc bike, you can have two different 100 cc bike. One bike which can ramp up from 0 to 100 kilometers per hour in 5 seconds, and another bike which can ramp up from 0 to 100 kilometers in possibly 25 seconds. So despite that both the bikes have got similar capacities, their ramping abilities are different, leading thereby to challenges during of system operation during this. And the challenges obviously, if the capacity is not available, 100, if the 100 cc bike is not available, or the 100 megawatt power plant is not available, then also it leads to frequency excursions. And here also, when the ramping ability is not available, also that also leads to a situation when these areas, this time, wherein the frequency excursions will happen significantly. You are true, both the factors would impact frequency in a significant way. But the impact has to be understood separately. This is the only point that I want to highlight.
Yes, sir. Understood. Thank you.
And obviously, as you rightly pointed out, the frequency challenges would happen at both ends. From 4 o'clock to 6 o'clock on one side, ramping up and ramping down from that period, and then again ramping up and ramping down. The key question, the key problem is that the ramping requirement in the system, both up and down, would significantly increase when you see these black plots vis-a-vis when you see these purple plots. This is the key thing that we need to focus upon. That opens up a new set of challenges on how system has to be operated. That impacts. You would have heard about the duck curve, which reflects the generation. So if you see the
May I ask,
generations happen. Yeah, please.
can this be correlated or by any way related to load shedding also?
Load shedding would obviously happen when there is not sufficient generation or ramping ability is not there. Both ways, load shedding would happen, obviously. And if you do not have those capacities, you will have to resort to load shedding. If it's something like you are driving a vehicle, it does not have the capacity, it is overloaded. Let's say if you are running a vehicle, it is overloaded, it will have limited capacity, it will ramp up very slowly, it will be a heavily loaded vehicle sort of thing. And that would eventually lead to a situation that either you offload some of the generation if you want to speed up, or the ramping up would happen at a very slow pace. Similar examples from any other such systems we can always quote. Obviously, in the case of power system, it would lead to challenges of frequency, load shedding, all those things would come up. Coming back, the net load shapes in the scenario of high solar, the duck curves that we see, which is very common term when we see how the demand would vary. So the duck curve would become more prominent. Duck curve is basically a reflection of the load or the net load in the system. So the duck curve would become more prominent, and it is becoming more prominent. This is what is being seen in different grids, which are becoming more and more dependent upon RE generation. So the type of reflection, this is a plot of 2012, and if you see, these are plots of 2020. This predominance of the duck curve becoming more and more steeper is visible in different grids across the world. And that is a similar scenario in Indian grid as well. So the challenge that will come up is, now this is the key focus, that even systems with adequate generation capacity, they would have adequate generation capacities, 100 gigawatt, 200 gigawatt, 500 gigawatt, but they would not have the capacity to meet the net load changes due to ramping insufficiency. That despite there would be 100 gigawatt, 200 gigawatt power plants, but ramping up or ramping down of generation capacity, that is not available, thereby leading to scenarios that you would have power plants, you would have those capacities in place, but they would not ramp up. This creates a problem. Ramping is one part. Another problem is the minimum up and down time of the power plants. You all understand that if a thermal power plant is switched off, if you want to bring it into on condition, into a hot condition from a cold condition, it takes a couple of hours, and the number of hours could vary from 4 hours to 16, 24 hours. So if a power plant is in a down state, suddenly bringing it up and ramping it up may become a challenge. So because of the minimum downtime or uptime of the power plants, there are limitations on uh, having the ability to provide that demand, fulfill that demand because of the limited ramping and up down capacities of the system. This is one of the key problems that the grid is now facing. So we started on this research a couple of years back. One of my PhD student was doing a couple of years back. He's presently doing a postdoc. But at that point of time in the Indian grid, it was not so strongly visible. Over the last 2-3 years, this problem has become more and more prominent, and that is why you are seeing a lot of new investments happening into the grid. Some of those which we'll be talking about. But overall, what this requires is the necessity to make the system more and more flexible in terms of the ability to meet the varying demand in the system. This is why we are focusing upon power system flexibility in RE rich grid because of the problems that are being caused by high RE penetration happening in the grid. I hope everybody, from even if it is a civil engineer or a computer science engineer, can understand the challenges that I am trying to highlight. I hope so. Why this big problem is becoming aggravated across the world, whether you talk of any part of the world, Europe, you see cases like Germany, significant deployment of distributed solar and wind, large number of households having those PV rooftop, and they are facing as high ramp as 10 gigawatt per hour and ramping down of 7 gigawatt per hour. So that is a very large ramping up and ramping down rate which is required from the power plants. Similar challenges in Colorado in US, where the wind power supplied more than 61% of the energy to meet the customer demand. Denmark, where because of high wind conditions, whatever is the demand, the wind power plants are producing much higher than or as high as 140% of the generation. If the demand is 100 gigawatt, they are producing 140 gigawatt of wind generation. So these type of situations do arise when we are shifting towards higher and higher RE penetration. And this is not something that is easy to handle because the key constraint of balancing the demand and generation at all points of time has to be followed by the system operator. This leads us to the challenge to understanding, to modeling, to focusing on the problem of power system flexibility, which we define as the extent to which a power system can modify electricity production or consumption in response to variability. It may be expected variability or it may be an unexpected variability. So whatever variabilities exist in the system, the question is how much capacity does the power system have in terms of its in the ability to modify the production or the consumption. This is the broader challenge. It is usually classified into two facets. One is the operational framework, which we call short-term operational flexibility. Another one is a planning framework problem, which we call as long-term flexibility requirement planning problem. Both have got different facets to understand. You would have those of you who come from electrical engineering or power system perspective. you understand that this short-term flexibility talks about optimal scheduling, optimal power flow, unit commitment. These are the type of things that we talk about in short-term operation. Whereas in the case of long-term planning, we start looking into the generation portfolio, what is the generation mix, and so on and so forth. So the two different type of problems. This is a short-term problem. This is a long-term problem. In the short term, we try to identify what should be the optimal scheduling. Scheduling would mean how much a power plant would produce at any given point of time. So what is the optimal scheduling of resources to meet the net load ramps of the system? In scheduling time frames, scheduling time frames would be from a few seconds to few minutes to few hours to few days to possibly a week or maybe a couple of months at max. This is a scheduling time frame. And when we talk about planning problem, this is in a long-term time frame, that what type of power plants we should invest into, whether they should be thermal, whether they should be hydropower plants, nuclear power plants. That is a perspective that we start focusing in long term, like few months to few years to even 10 years, 20 years down the line, what type of generation mix we should have. To understand this problem, possibly those of you who come from power system background or electrical engineering background can possibly understand easily. The problem now becomes how to assess what is the flexibility requirement, and thereafter what are the mechanisms to enhance the system flexibility. Both points have to be focused. First thing is to quantify which system has got how much flexibility. And second part, how do you develop those mechanisms so that whatever flexibility is required, we can enhance that flexibility. This is slightly mathematical, probabilistic distributions, but it is not so difficult to understand. To measure the power system flexibility, there are certain indices which we have focused upon, which have been developed. One is, we'll possibly understand as I go through those. One is the ramping limit. Ramping limit is the maximum change in power output that a resource can make from its operating point in a certain time. Meaning that what is the maximum change that the system can have whenever it is operating at, let's say, 110 gigawatt. What is the, let's say this is 100 gigawatt, it is operating at this point. The ramping limit is pi max to pi minimum. This is the ramping limit of the system. Then this is the capacity of the system, power capacity, limitation on maximum power, minimum power output of the resources. So if this is the generation of the system at any given point of time, this difference plus and minus indicates the capacity of the system. The ramping limit is indicated by rho max and rho minus, where rho is the slope of this, how much change can happen in the generation over a given period of time. So what is the maximum ramping capacity and the ramping up and ramping down capacities of the system. So these are two different parameters. One is from 100 gigawatt, what is maximum and minimum where it can go. Maybe from 100 gigawatt, it can go to 110 gigawatt up, 110 gigawatt down, or 90 gigawatt to bottom. Just give me a second. I have an urgent call to take. Just give me a few seconds. I'll be back. Just give me a few seconds. Sir. Sir.
Participants, please be here only. Actually, our expert had some urgent call, so he is there in the meeting only. He'll restart soon. Please be here only and have patience, please. All the participants are requested to please be here only. Please don't leave the meeting. Actually, sir had some urgent call, so he'll be back right now. Meanwhile, I wish to say that the attendance link has been shared in the chat of this meeting. So you may go there and fill that Google form to mark your attendance for this session. Actually, some of you might have some problem today during joining the meeting. So actually, this is because of some settings of this WebEx tool. So we are trying to work on it, and it will be rectified today. And from tomorrow, session first onwards, you will not have this problem. You will be able to let in directly without making us by making us the let in. Our expert is live. Please be here only in the meeting. Actually, he had some urgent call, so that's why he has requested 2-3 minutes break for from the session. So please be here only. The session has not been over yet. As far as joining of this meeting is concerned, some of you might have the problem today during the joining through WebEx. So this is because of the settings of that WebEx. Actually, we have some problem there, and we will rectify it by today. And from tomorrow onwards, we will be directly let in without receiving our permission. You simply get in without. There is no need to make each and everyone let in by our side. You will be able to join directly. One more thing is that you should mark your attendance by filling that Google form, which is being shared in this chat of this meeting. Every session you will have the Google form that will be shared in this chat of this meeting, and you can go there and then fill. So once again, I request you to please be here. Actually, sir has some urgent call, so he might be joining within 2-3 minutes. Although he is there in meeting only.
Sorry, I hope I'm audible. Dr.
Yes.
Ganesh. Dr. Ganesh, I hope I'm audible. Any of the participants, if you can hear
Yes,
me.
I'm audible.
Okay, just hold on for a second. Yeah, sorry, I had an urgent call to take. Thanks for your patience. I'm back.
Yes, sir, no problem.
I hope you can see the slides, Dr.
Yes, sir,
Ganesh.
it is visible clearly.
Any of the participants?
Yeah, it's clear.
Thank you, thank you, thank you. So we were in a situation trying to understand what are the indices of flexibility. So this is some mathematical modeling to understand what are the ramping limits, what are the capacity limits, what is the overall energy capacity, and what is the response delay in responding to situations. So these are the type of facets which decide whether the system has got flexibility or not. So different parameters, they indicate different type of flexibilities into the system. So whether it can ramp up or ramp down fast, whether it has got the capacity, whether it has got the energy to deliver the required energy demand, and what would be the response time in when it is expected to reach the deviations and meet those deviations in the system. This is a general understanding that has to be made. Now, all this flexibility has to be provided in the grid by different sources. So we need to identify what would be the sources from where the flexibility can be sourced. Obviously, whatever is the total available flexibility, we only require a small part of that flexibility, and which can be sourced from various sources. What are those sources and how do we do it? And in case there is a lack of flexibility, how do we quantify it? So typically we have got three variables, three parameters to measure that. One is that if you have got a lack of flexibility, you would have to face renewable curtailment, and that is quantified in terms of megawatt hour, load curtailment in terms of megawatt hour, or ramp insufficiency in terms of megawatt per unit time, per unit change in time. So these type of metrics also people have started focusing upon. The ways by which we meet flexibility. Why do we need to focus? Because when we are putting in more and more renewables, we need to develop systems by which flexibility can be ensured into the grid. What are those mechanisms to bring in flexibility? I hope you can see this slide. Any participant, if you can just respond.
Yeah, it's clearly visible.
Okay, thank you. So this is a paradigm which reflects the resources by which we can enhance the flexibility. This is a very wide picture, gives a very wide picture of the options that are available. Again, this is important when we are going in for more and more renewable penetration. These are the areas that we need to focus upon, and one or more of the solutions we need to adopt so as to fulfill the requirements of flexibility in the grid. This could be by improving the operations, providing demand response, improving the grid infrastructure, putting in more generating plants, putting in storage, and going in for sector coupling. We'll touch one by one, one or more of these points. When we talk about improved operation, we talk about increasing the scheduling granularity. Like rather than scheduling the system for 15-minute interval, we start focusing on every 5-minute interval. So that helps us to address the demand supply balance in smaller time frames, requiring a focus of the system operator of every 5-minute time scale to ensure that the demand and supply are balanced. Forecasting has to be improved so that in day ahead, in real time generation, forecasting has to be improved so that understanding the forecast, one can make quicker decisions. New market products have to be brought in, which allow uh, providing payments for those type of generators which can handle those uncertainties, which can handle those scheduling requirements, which can handle those flexibility requirements in the system. That is one way of handling it. Shorter gate closure, that is when the markets have to be closed prior to the delivery. So more and more market products are made available so that more generation is available, more sufficiency of generation is available in the system through different market products. This is something that we talk about when we talk about in electricity markets. As far as demand response is concerned, demand response is a much talked about topic, and it is the ability for demand to respond in response to certain economic signal, in response to certain tariff, in response to certain pricing. It is a very cheap option, which enables the demand to be shifted or switched off, on, off, or on according to price signals. It is highly reliable and it is quite manageable as well. So this is one of the ways to provide flexibility to the grid. Obviously, you would have heard about all these mechanisms in which we demand side management mechanisms by increasing efficiency, providing demand response, strategic load growth. We can have market-based programs for those, reliability-based programs, variety of demand side management technologies, they exist. As far as generation is concerned, we can focus upon lower minimum load to provide system flexibility, higher ramping rates from generators to which would provide more flexibility, decreasing the minimum operating point of a generator, that is the lower minimum load, decreasing the minimum uptime or downtime of the generators, that also increases the flexibility, shorter startup time, which is 4 hours, 8 hours, 24 hours. We could reduce those by improving the technology of the power plants. So these are some of the flexibility options on the generator side. Systems with large hydro and gas, they are more flexible, so they can provide more flexibility, ramping capabilities when our dependency on thermal and nuclear is obviously that is restrictive in terms of providing flexibility. Flexibility indices, they would help us to understand what are the requirements. These indices that we talk about, they would depend upon the typical parameters. What is the minimum up down time, ramp up ramp down time, operating range, startup and shutdown time. And usually economic efficiency of coal power plants, it is designed to provide maximum efficiency when it is operating at 80% annual capacity. So if it is a 100 megawatt coal power plant, the maximum efficiency of the power plant is when it is operating at 80%. So we need to retrofit those power plants so that they provide a similar level of efficiency even when they are operating at lower capacities, so that system efficiency, the generation efficiency, is maintained. Providing flexibility options from generating power plants, different countries have already, they are working on it. China, India. India is typically focusing on reducing the technical minimum of those power plants from 75% to 55%. That means you allow those power plants, thermal power plants, to operate at 55% as and when required. Otherwise, usually they become inefficient when you are operating at lower capacities. Similar retrofitting is being done in several countries across the world. Another flexibility option that people have started focusing is energy storage. You would have heard about it. Even last week, when they talked about putting up a solar park in Pugal, Bikaner, in association with that, there is a lot of battery storage that is coming up. And obviously, that provides flexibility in terms of fast ramping capability. Though it is capital intensive, but the investment in this segment is increasing. It is likely to increase over a period of time. Another option that could be, apart from battery storage, could be other storage options also. Pumped storage is being talked about, compressed air, other flow batteries, solid state batteries, thermal energy storage also people are talking about. So these are technical solutions that people can adopt to fulfill to have storage capacities in the system to provide flexibility into the grid. So all sort of storage technologies, each one having different characteristics in terms of densities, in terms of efficiencies, in terms of cost economy. So different generation technologies, different storage technologies having different type of characteristics. Some of those have become economically viable, like battery storage is economic viable, pumped storage is also picking up, and so on and so forth. There are wider applications for battery storage. So battery storage not only provides ramping capabilities, which you will see There are a variety of services that this storage can provide. It can provide bulk energy supply. It can provide ancillary services like load following, voltage support, black start, frequency regulation, spinning reserve. So all sort of ancillary services support can be provided by energy storage. It can provide quality of power, reliability in power. It can help to firm the renewable capacities. It can help to shift the RE generation capacities, availability of RE generation. So depending upon the type of requirement in the grid, the utility of those energy storage can be variety of those, and that is where the value from those battery storage energy storage can be secured. Obviously you would have seen this graph, a variety of storage options, each one having different energy capacities and power capacities. So different supercapacitors would have a different characteristics. SMEs, the superconducting magnetic energy storage, would have a different operating range. You would have pumped hydro storage having larger capacities in terms of both in terms of energy as well as power. Thermal energy storage somewhere lying in between. So depending upon the type of technologies, their ability to provide energy as well as the power would vary. Sector coupling is another interesting area to focus upon, which allows different energy sectors like electricity to be coupled with other energy sector like heat, like gas, like oil, interconnecting those, or connecting sectors like the energy consumption is building, industry, and transportation. This brings in value in terms of the ability to shift the generation as well as the load and the storage as well. So these type of facets are also being talked about when we try to see overall energy perspective. And this, in terms of sector coupling, we talk about integrating the electricity network with the hydrogen network, with the gas network, the heat network, and the cooling network. So different sector coupling mechanisms can be adopted because each network has got different ramping capability, different storage capacities. So the benefit of one or more of those vectors can be utilized to mitigate the requirements in other energy vectors. This is the beauty of sector coupling. And over the last 4 or 5 years, people have started focusing upon both the operational perspective as well as planning perspective of coupling different energy sectors. These provide a variety of flexibility options in terms of short-term flexibility challenges to mitigating long-term flexibility requirements. When we talk about short-term flexibility options, obviously some of those points which we pointed out, frequency, inertia, primary frequency responses, these are areas which come under the domain of short-term operation challenges. These also can be taken care of by the flexibility options. Balancing in terms of minutes, load following in terms of minutes, hours, that also can be taken care of by different options. Then moving on to hours and days, the problem comes down to unit commitment, resource scheduling. Sector coupling helps in these cases, and other storage options can help. When we go over to a longer time frame like months and years, different mechanisms like hydrothermal scheduling, resource planning, these help. Transmission expansion planning, these help to provide sufficient flexibility into the grid so that the flexibility challenges, the ramping challenges, they can be mitigated. So the type of research that people need to focus upon is of wide variety. You may be working on a short-term time frame in terms of inertia, frequency. You may be working on long-term time frame of planning perspectives and intermediate time frames of operational planning as well. So depending upon what type of time frame where you are working, the economies involved, the market products involved, the technologies that are available, and the type of operational strategies that you can adopt, improved operation, demand side, generation, storage, or planning. So all these things have to be focused upon from a very broader perspective when we are trying to address the challenges arising from high renewable penetration. Obviously, when we start focusing on these, we need to focus upon improved market design, increasing the granularity, having improved ancillary services, having capacity markets, improving the system operation perspectives, better coordination between transmission system operator, distribution system operator, better forecasting mechanisms, improved new business models like aggregation, peer-to-peer. All these things, they come under these perspectives. Enabling technologies could be developing of mini microgrids, virtual power plants, blockchain technologies. All these things, they come under the spectrum of those technologies which can be adopted to provide those services in a more flexible way. Broadly speaking, the key takeaways from this understanding is to focus upon one or more of these mechanisms in terms of improved operation, in terms of providing demand response. So as you see, improved operation is a cheaper, is a cost economic mechanism. Demand response is also a cost economic mechanism to provide flexibility. As you go down the line, these are costlier options to exercise uh, in the perspective of providing sufficient flexibility into the grid. If you do not do it, obviously the cost of either you are providing poor power supply, or the cost of the alternate cost of providing those services would be significantly high. So all these facets people have been talking about, and the facets are not only limited to electrical energy. It is the challenges they relate to mechanical, because when we talk about energy, people from all perspective, whether they are coming from mechanical, whether they are coming from chemical or other spectrum also, they need to be understood. Their perspective needs to be understood. Even people coming from civil engineering background, they also need to be their energy requirements when we are doing the building design, their energy requirement have to be understood. So all these type of studies, they help you to understand a variety of assets wherever energy is required. Broadly speaking, we need to focus upon the operational perspectives. We need to think about institutional perspectives in terms of new market products and scheduling frameworks. And we need to think about long-term planning in terms of which generation sources we need to focus upon, what should be what are the operational parameters, and how do we, when each type of generation technology should be brought in, so that whatever RE penetration is happening, we are still being able to handle the grid in an efficient and robust way. These are some of the references, but I think I'll be happy to take up questions. We are running slightly behind schedule, but I'm open to questions if any, please. Yeah, please.
Yes, thank you. Thank you very much, sir. So, participants, if any of you have any question for this session, they may directly ask to sir.
Sir, good afternoon, sir. Dr. Rohit, sir.
Yeah, I'm able to hear.
Sir, Dr. Chauhan is speaking from Jabalpur, sir, Gyan Ganga Institute, sir.
Yeah, please.
Sir, during your discussion, you discuss about the flexibility actually, and one of the key actually, that is demand response actually, by which we can achieve this actually.
Yeah.
Sir, can you tell me about in India, is any state implementing this concept regarding to get the flexibility power system actually? Because I am not getting some practical data actually.
About demand response.
Yes, can you tell me about in context of India actually?
There are states like Maharashtra where they have implemented demand response specifically for industrial consumers. Similar exercises have been taken in Delhi as well, because there are private suppliers there. They also are focusing on these segments. Practical data obviously has to be secured from those utilities only. But yes, demand response mechanisms are in place, at least in these two urban populations of Mumbai and Delhi, specifically the large sized consumers, industries. They do follow those. And even beyond that, when we are putting in smart meters, we need to take into consideration that smart meters would eventually lead to smarter tariffs. And when we are adopting smarter tariffs, obviously demand response would come into picture. That would be there. It'll come as more and more smart meters are getting installed. That will happen.
Okay, if we are taking the example of this MP state, actually, they are taking initiative to install these smart meters. Even they are not implementing this concept, actually, matlab, demand response. That is the participation of customer, actually. So
This will
even
happen over a period of time. This will not happen immediately. Demand response has got many facets. This is not a single facet. But if you are talking about providing response to in terms of tariff design, that is one of the ways. Industrial consumers are happening at some of the places, and eventually, as soon as you have those smart meters in place, obviously smarter tariffs would get implemented over a period of time. Maybe if not immediately, down the line, 1 or 2 years down the line, it will happen.
okay, sir. Sir, one more question, actually. May I ask you, sir?
Yeah, please.
Sir, can you tell me what is the benefit to implement this demand response in the industry? Actually, you quote one example of MP, this Maharashtra, actually.
Uh, uh, Usually, the benefit is that
So matlab,
benefit
what
for
as
whom?
yes.
Please, can you clearly ask the question?
Even during the demand period, why the industrial consumers will participate in demand response, actually? How they respond, actually?
It all depends upon what is the type of economic value that you give it to them. If you are providing them economic value, if the tariff design is suitable, they'll respond. Obviously, the process industries would not do it. Those industries which require a continuous electricity supply, they will not do it. But those which are not process industries, they can obviously respond. They can obviously respond, and depending upon the tariff design, they can respond. Though the quantum of response is limited, but still it opens up a window where if the tariff is, let's say, during the evening hours from 5 to 11 p.m., if the tariff is double that of what is the daytime tariff, obviously they'll respond. They would respond.
And during your presentation, you suggested that it is one of the best way, actually. And why we are thinking other ways, those are very typical and cost effective, actually. And it is one of the
Uh,
best way. Even you
yes,
are discuss about this energy storage also, actually.
yes.
So
The
then,
reason
matlab,
is,
it's my concern.
hmm,
Then this technology will obsolete, and why we are searching about other technologies. Actually, these are cost effective and very typical, actually, and also the environmental concern if we are talking about energy storage, actually.
hmm. The reason is the whole of the power system is not driven by specific technologies. It's everything is running uh, as per economics. Presently, until and unless we have got appropriate smart tariff in place, we don't have an option. Earlier, what was happening was maybe 3 to 4 years back, that was somewhere in 2022, 21, when we started pointing out this issue that the grid does not have sufficient storage capacities, the planners were not very keen. They were not interested in putting in so much of money in terms of storage. But when they realized that the problem is becoming big and the smart meter rollout would take time and the smart tariff would take time, they do not have a choice as of now. So the immediate solution was to put up more and more batteries. So despite not being environmental friendly, we don't have an immediate solution. That is why you adopt it. And more so, over a longer period of time, you cannot be sure of. I'm saying that demand response is a good option, but whether it would get implemented, whether the customers would accept it, whether the state utilities would be able to adopt it or not. These are questions that nobody can answer as on date. There are a variety of options. Which one? These are technical solutions, but which one the states would adopt, which one the distribution companies would adopt, it would depend on their own policy making. So we are nobody to decide. So we, as technocrats, we can only suggest those options. Eventually, it is the utilities that we have to adopt it. It is their call, depending upon how they see it. Some of the states may adopt it, some of the states may not adopt it, and this will happen. Rajasthan is going in a very big way in terms of putting in energy storage. It may well happen that it may not adopt demand response strategies. It may not. It depends. Our role as technocrat is to open up all the possible options. It is the policymakers, those will have to take a call.
Okay, so rather than India, can you suggest another country which is implementing one of this concept in very best way?
Demand response mechanisms. I
Yes.
think there are demand response mechanisms in US industry. They have adopted it. Even in European countries also, UK has adopted it. Demand response tariffs are there in place. Yes, they are there in place.
Okay, sir.
Yes.
Thank you very
Yeah.
much. Thank
Yeah.
you.
Please. Anybody else? Any further questions?
Thank you for your kind reply, sir.
So any other participants, if any question, they can ask. Sir, if you would be able to see the chat box, if there is any question. Actually, I'm not able to access the chat here in.
Okay. Just let me see.
Rather, if any participant wish to ask, they can directly ask to sir.
There are no questions. There are no questions in the chat box.
Okay, all right, sir. Thank you. So, thank you very much, sir, for a wonderful session and a
I
healthy discussion.
can. Let me just check. I think I'm going down double stairs. Just let me check if there are still. Let me check if there are any questions. No questions. Yeah, please.
Okay, all right, sir. Thank you very much for sparing the time for this FDP. Actually, this was very fruitful and a healthy discussion has been held at the end also. So this session was full of information, and I personally have got very much insight about everything which has been presented.
Sir,
So once again, I am very much thankful to you, sir. And now the session is over, and we can leave the meet. And about the document, I'll contact you further, sir.
Thank you.
Okay.
Thank you,
Thank
everyone.
you.
Thank you, everyone.
Thank you, Rohit, sir, and thank you all the participants also for listening patiently. Thank you very much.
Thank you very much, sir.
Thank you.